Okay, we're still in 8.3 talking about applications to physics and engineering. This one is fundamental. From my experience as a person who took courses at ARC at some point, I took Physics 410, Mechanics of Solids and Fluids, and this was one of the applications that we talked about. It's actually fundamental to anything that relates to things that don't move and things that do move, because really what we want in terms of when we're building systems, for instance, for engineering, we want them to be in equilibrium. And that's not only equilibrium of forces in the rectilinear sense, where, left to right, up, down, but also in rotational motion, okay? And this is where we're going to talk about that to some extent. So in this video, our objective is to define and calculate moments and center of mass for a planar lamina. A planar lamina is just a continuous solid object that's flat, okay? But Latin words because fancy. We're going to start, though, by talking about a simpler form of this, which is discrete systems of particles. So we're going to consider a system of n particles, n being just any finite number. Oh, that's already n, sorry, particles. Each has mass m sub I, little m sub I, and a location x sub I, y sub I, okay, relative to some origin, which I'm going to denote as 0, okay? And what we define the center of mass, or the centroid, which is a location about which the system would freely rotate as if it was all one object. And to understand what we're talking about here, I have a simulator that I'm going to show you here. It's actually a very cool looking application. Here we are. So this is from simbucket.com. It is a center of mass builder. And the idea here is that you pick a different grid point that represents a particle with a specific mass and a location. So if I put one particle right there, then I have a system of one particle, and of course its center of mass is its location, because it's just one particle, right? And so if I put the little pin right there, and I press the go button, it doesn't do anything. It doesn't move, because there's nothing interesting about this. So we're going to reset that. And let's consider now 2 particles. Or maybe let's do 3. Let's do 3 particles so that I can pin this properly. So that little target look is representing the center of mass. And so naturally we would expect that by putting the pin right there and letting this go, it'll spin freely about that point. And we get, there's no, it's in equilibrium. So rotationally, what we're saying is all the forces cancel out. And, well, that's not very clear because I didn't pin it properly, but you can tell that really it shouldn't have a preference. Like, it shouldn't flip over to one side wildly and have a preferred location. But we can make that for as many particles as we want. We're assuming that all these particles weigh the same. Okay, and there it is, all freely rotating about that point. Let me show you what that would look like if it had been somewhere else. You see how there's a preference there for the heavier side of the system. And then it will be out of equilibrium until it finds an equilibrium point. All right, so that's enough of that. Let's go back to the idea here of center of mass. How do we calculate center of mass? So there is a formula for this given a system of particles where the x location is given by the sum of all the products m sub I, x sub I, divided by the sum of the mass. And we call this, for our shorthand, our numerator is going to be capital M sub y divided by little m, where, little m is the total mass. So these are equal to each other, and these are equal to each other. And capital M sub y is called the moment about the y-axis. It's a measure of how much the system of particles wants to rotate with respect to that y-axis. And similarly, we define for the y-coordinate, you may have guessed that there's a symmetry here. You take the sum of all the products of the masses and their y-coordinates and divide by the total mass. And this is equivalent to the moment about the x-axis divided by the total mass, as before. So this is the propensity of the system to rotate about the x-axis. And we can do this, we can calculate for any given fixed system of n particles the center of mass using these formulas. When we pass this along to continuous distributions, things get complicated. Let me explain why. So I'm going to draw here what is going to be representative of my planar lamina. My planar lamina is going to be the area underneath a curve. So this is some curve y equals f of x. Here's A, here's B along the x-axis, and here's the y-axis. Okay, so this region R is my planar lamina. Let me actually highlight those letters, that word, because it is a vocab term here, yes. A lamina meaning it's just a flat sheet, right, of uniform density. This is important. If we don't assume uniform density, then we have to adjust the calculations, and that's beyond the scope of this course. And our uniform density, we're going to call that rho, defined by the area under y equals f of x. And for simplicity, we're going to suppose that f of x is a positive function. It never crosses the x-axis. So then that region R, we can break this down into a Riemann sum again. We have some rectangle here, an approximating rectangle. And for that rectangle, right, we can find the centroid pretty easily. So, and by centroid I mean, of course, center of mass. So center of mass is the same name, or a different name for the same thing. So for the ith Riemann can't spell today, sorry. Rectangle in our approximation of this area, the centroid is x sub star is going to be, x sub I star is going to be the midpoint. Of x sub I minus 1 and x sub I, which is, of course, x sub I bar. We already had that notation for it. And the y-coordinate of that approximating rectangle is half the height. So 1/2 f of x sub I bar, okay? Then, in the limit, okay, because we're adding, not because we're adding these up, but because the centroid, right, if this is the centroid of the rectangle, right, we should expect that something similar happens in passing to the limit. So what we're actually looking at here, though, is the center of mass is going to be the integral from a to b of the uniform density rho times x f of x dx, okay, divided by the integral from a to b of rho f of x dx. Let me break down what is happening here, okay? So why do we need rho? Rho is the density. And so since we're looking for the mass, we need to multiply the mass by the density. So, the volume by the area by the density. And this, similarly, to find the moment about the y-axis, we'll need the rho there as well. Now notice that because rho is constant, it's a uniform density that we're looking at for this planar lamina, they cancel out. So we actually don't need a trace of that. Unfortunately here, though, unlike with our previous calculations, there's no symmetry that happens nicely for y bar. And that's because of the, really fundamentally what we're talking about is these terms here, we're going to be multiplying those by f sub this is what allows us to, this isn't part of the calculation for that specific centroid, but we're multiplying it by that to get the proper moments, okay? And so for the y-coordinate, then we're looking at the integral from a to b of 1/2 f of x squared dx. That's the moment about the x-axis, divided by the integral from a to b of f of x dx. And of course, this redefines our moments. This is the moment about the x-axis over the total mass. Or it's equivalent to, because we cancel out the densities. We can generalize this to lamina between two curves, but we don't need to talk about that right now. All I will say that then is that for in a region between y equals f of x and y equals g of x, then m sub y divided by rho, we're just going to instead do x times f of x minus g of x dx. And for the moment about the x-axis divided by rho is going to be the integral from a to b of 1/2 f of x squared minus g of x squared dx. All right, so that's a lot of formulas. It's a lot of talking about, something that isn't a concrete example yet. But I would like to go over a concrete example here. So our example, let's find the center of mass of the lamina defined by the quarter circle of radius 3 in the first quadrant. Okay, so before we can begin to parse this, let's draw the situation. So in the first quadrant, I have here my lamina, which looks like this. And it's got a radius of 3. So this function that defines the curve is y equals the square root of 9 minus x squared. Okay, not bad. And our center of mass is somewhere in here. We'll find out the exact location. One really important helpful piece here is the mass. So remember that we can find the mass as rho times the area. And the area of this is 1/4 of a circle. So it's 1/4 pi times 3 squared. So whatever the density is, it's going to be the density times 9/4 pi. Okay, so that's going to be helpful. That's going to allow us to focus just on the moments. Okay, so let's actually calculate the moments then, because the x-coordinate of the centroid, the center of mass, is going to be the integral from 0 to 3 of x times f of x, which is the square root of 9 minus x squared dx, okay, all over 9/4 pi. I'm deliberately leaving out the rho because they cancel. Okay, they always cancel. So we can write this more simply as 4/9 pi times the integral from 0 to 3 of x square root of 9 minus x squared dx. And here you can use a substitution. This one's not too bad. So we're going to let u be 9 minus x squared. Our du is negative 2x dx. And if we go ahead and replace the limits of integration as well, then we'll get the integral from plug in 0, you get 9. Plug in 3, you get 0. X, in order to pull that x times dx out, we're going to have to multiply by negative 1/2 du. U to the 1/2 du. Okay, very good. Okay, and then I can pull out the negative 1/2 there. So that'll cancel with the 4. We'll get negative 2/9 over 9 pi times the integral from 9 to 0 of u to the 1/2 du. Okay, and so by passing that to the antiderivative, 2/3 u to the 3/2, evaluated from at 0 minus the evaluation at 9. Don't forget the negative 2/9 pi in front, and then here at this point it's algebra, right? So let's go ahead and just finish out this calculation. So negative 4 over 27 pi times 0 to the 3 halves minus 9 to the 3 halves. 0 to the 3 halves is 0. 9 to the 3 halves is 9 times 9 halves. Oh, and that's a negative canceling with a negative, by the way, so it's going to be positive now. And 9 times negative 9 1/2, that's 9 times 3, so that's 27 over 27 pi. Lo and behold, we get 4 divided by pi, which is roughly like 1 point something. It's not very important that we know that, but that's in the range of 1.2 or something like that. Okay, by symmetry, it stands to reason that y bar should be the same. Why? Because there's a natural kind of nice symmetry about the shape, right? Where we know that it's symmetric about the line y equals x. So it makes sense that y bar should be in the same location as x bar relative to the relative to the y-axis. So, but let's just go ahead and do the calculation because it's different, right? So remember that y bar is going to be 4 over 9 pi, because we're dividing by the 9 pi over 4, times the integral from 0 to 3 of 1/2 times f squared. So 9 minus x squared dx. Okay, pull out the 1/2, we get 2 over 9 pi times the integral from 0 to 3, 9 minus x squared dx. And that's going to be 9x minus x cubed over 3 from 0 to 3. 2 over 9 pi in front. And then evaluating that at 0 gives us nothing, so we just need to evaluate at 3. So 2 over 9 pi times 27 minus 27 over 3. And that ends up being, I'm just going to continue this on the same page because there's so little left to say here. That ends up being 2 over 9 pi times 18. And very nicely, we get 4 over pi. Okay, so the center of mass is the point 4 over pi, comma, 4 over pi. And there it is. Okay, so these calculations can get kind of onerous, but there's an opportunity as well here to explain any symmetry to help guide our intuition or to even help us find the calculations and simplify them as well.